In this video we'll look at some of the equations that describe matter when matter exhibits its wave nature. This is a rather unintuitive and bizarre part of physics, but the equations that describe this behavior are surprisingly simple. The equations, before they were tested, were dreamt up by DeBroglie, and they're based fundamentally on this diffraction pattern that was exhibited by electrons as they were passed through aluminum foil. And when that wave interference pattern emerged from electrons, which are thought of and known to be particles, but from this empirical evidence we see the wave behavior of electrons. So this was the initial fundamental evidence for the wave nature of matter, given that X-ray electromagnetic radiation had already been established to have a wave and particle nature, and in this evidence of the interference pattern, the wave nature is observed as there are points of maximum constructive interference of the X-ray waves and also regions of maximum destructive interference, wherever there is no X-ray wave amplitude detected on the X-ray film. So because the same pattern emerged from the beam of X-rays shot through the same aluminum foil, we can infer that that's evidence for wave behavior of the electrons. Of course, this has been repeated tens of thousands of times through different metal lattices with different wavelengths and frequency, light as well as matter particles. But there are limits to the detection of these matter waves. The fundamental limiting factor is the mass of the matter particle. So once the mass of the matter particle is beyond around 10 to the minus 27 kilograms, electrons are 10 to the minus 31 kilograms, we don't have and will not ever have any type of device that can detect this type of wave nature of matter. And this will be seen in the equations developed. So to see just what could be the wavelength of a particle of matter, a matter wave, DeBroglie took the already established equation of Planck, the energy of a quantum as hc over the wavelength, and the from nuclear physics equations of Einstein, that the change in nuclear mass times the speed of light squared would be the change in energy of the system of nuclei undergoing either nuclear fusion or fission, and that's often simplified to just E equals mc squared. So setting the two energies equal to each other, not knowing whether anything fruitful would come about from this, and in addition using v for the speed of the particles of matter instead of c, which is the constant for the speed of light, because nothing that has mass, like a particle of matter, can travel at the speed of light. So just using the more generic speed v, hc over lambda becomes hv over lambda, and that's v for speed, not nu for frequency, equals mv squared. So not quite the kinetic energy formula, but the same units as energy. And those two equations were married or equated, and from that you could see that one of the v's drops out, and you get this equation, h divided by lambda equals mv. And as an aside that you'll see later, that means for a matter wave, since mv is momentum, we have an expression for momentum in terms of the wavelength of the matter. So for matter or particles that actually have mass, the matter wavelength is equal to Planck's constant, which is insanely small, on the order of 10 to the minus 34, divided by the momentum of that particle. So it depends not only on the mass of the particle, but also on how fast it's traveling, which is guaranteed less than the speed of light. So there's the relatively simple equation for the matter wavelength. It's just a constant, Planck's constant, divided by the mass of the particle of matter times its speed. So look at the units. The units of Planck's constant are joule seconds, so that's kilogram meters squared per second squared times seconds. And mass is kilograms in the denominator times velocity, meters per second, or speed. And the kilograms cancel. One of the meters cancels. This second in the numerator of the numerator cancels with one of the seconds in the denominator of the numerator, and then the other seconds cancel. And the only unit remaining is meters, which is the unit for length, or the wavelength of matter. The other comment is as far as magnitude. H in the numerator is on the order of 10 to the minus 34, and the denominator, let's say the mass of something is 1 kilogram and it's going at 1 meter per second, the wavelength of that 1 kilogram, let's say, I don't know, basketball or something like that, that's being thrown at 1 meter per second, the wavelength would be on the order of 10 to the minus 34 meters. And there's no device that could ever detect such a small wavelength. There's no film that could ever measure that insanely small peak-to-peak wavelength or anything like that. So it's physically impossible to detect matter waves that are not large enough. So in order to have this ratio be large enough to be detected, you need something on the order of a very low mass particle in the denominator, around, say, 10 to the minus 30, somewhere around there, and something that's not traveling too fast. So let's say on the order of 10 to the 5th or 6th. So there you would have a wavelength on the order of 10 to the minus 34 divided by 10 to the minus 24, around 10 to the minus 10 meters, which is around the wavelength of an X-ray or a gamma ray, which certainly are detectable. So that's why there's a physical limit on ever physically detecting some matter waves, although because other matter waves can be detected, we just inductively reason that there at least is a theoretical matter wavelength for any moving piece of matter, no matter what its mass. One important warning: do not ever apply or use DeBroglie matter wavelength for photons or electromagnetic radiation. Photons have no mass, no rest mass, and this equation does not apply to anything that's a photon. So when you're asked for a DeBroglie wavelength, you must automatically be searching for the wavelength of some particle of matter, an electron, a proton, a neutron, some particle of matter. On a related note, but a completely separate question, we can come up with another version of Planck's equation relating the energy of a photon to its frequency or wavelength. This time we'll focus on the particle properties of photons or electromagnetic radiation that have no mass, or strictly speaking no rest mass. There's something called relativistic mass, which is beyond the scope of this course. But anyway, the equations that can be married or combined again to see what this relationship is that the energy of a photon by Planck's equation is h times the frequency of that electromagnetic radiation. And from Einstein nuclear physics, we have the energy is equal to mc squared, but here we know that the mass of a photon doesn't exist, so perhaps there is a way to take the mass out of this equation for photons, because we can't put 0 in there. No photon would have any energy then. So equating the energy term in general and applying it to the energy of a photon, we see that one of the c terms, constant, speed of light, drops out, and we get h over lambda equals mc, which is mass times speed, or mass times velocity, momentum without the direction. So we can't exactly call this mass because it's a photon, so we'll just cheat a little, not really cheating, but semantics, we call it the virtual photon mass, and we call this m times speed, or mv, or for light, mc, the momentum of a photon. So here is our expression for the momentum of a photon. It's just Planck's constant divided by the wavelength of the photon. The wavelength of EMR associated with a particular energy photon. By units at least, we should get the units for momentum, which would be a kilogram meter per second, mass times velocity. So Planck's constant divided by wavelength, one of the meters cancels and one of the seconds cancel, and you do actually get momentum units, even though a photon has no mass, kilogram meters per second. So at least using quote-unquote virtual mass, we get units of momentum. And there's one more equation we can come up with here. The energy of a photon in terms of its momentum. The momentum it physically imparts to, let's say, electrons, as electrons crash into and absorb that photon energy. E photon equals mc squared. So if we factor out an mc, the momentum of the photon, we have leftover c there as a multiplier. So energy of the photon is its momentum of the photon times the speed of light, which, since we already solved that momentum of a photon is h over lambda, we have the familiar Planck equation, hc over lambda is energy of the photon. So this is not DeBroglie wavelength or anything like that. DeBroglie wavelengths are for matter waves. This is for photons. We can at least express the momentum of a photon in terms of its wavelength. And as you see, it's inversely proportional to the wavelength. As expected, shorter wavelengths have greater momentum photons. Longer wavelengths, like infrared, radio waves, have much less momentum per photon.